Now we recognize that we will have some problems if we use non-stationary variables in linear regression analysis. So it's quite important for us to have some tools to identify non-stationary variables. The test that we are going to introduce is called unit root test. So suppose we have this AR1 process, and the equations show on the slide, yt equals rho times yt minus 1 plus vt. It will only be stationary when the absolute value of rho is less than 1. So the null hypothesis that we would like to test is whether rho is equal to 1 or not. And we call this test as a unit root test because of the null hypothesis that we have. Dickey-Fuller test is most commonly used one for this purpose. So starting from this slide, I'm going to give you the details of a Dickey-Fuller test. The test equation is as follows. Instead of testing whether rho equals 1 directly, we make some transformation. We subtract yt minus 1 on both sides of this equation. So left-hand side, you have the first difference of yt. Right-hand side, you have rho minus 1 as the coefficient of yt minus 1. So we rewrite it as a gamma. Then we will test whether gamma equals 0 or not. The reason that we make this transformation is because we can make use of the standard procedure in statistics software, because by default, all the statistics software will test the null hypothesis of whether a coefficient equals 0 or not, instead of equals to a specific value. So it's easier, operation-wise, it's easier to implement. So we test whether gamma equals 0 or not, and that's equivalent to a test of rho equals 1. We also have some variations in terms of test equation that we have. So for example, here we don't have a intercept term, but we can add an intercept term into the regression model, and we can also include a trend in it. On top of that, we can also include the lagged terms of the dependent variable in this equation. All of those variations serve one purpose. That is to make sure the coefficient estimate of yt minus 1 or the estimated value of gamma is reliable. So if you have any variables, important variables that are missing from your test equation, or if you have an autocorrelation problem, the coefficient estimate of yt minus 1 is not going to be reliable. In other words, the test of rho equals 1 or gamma equals 0 will not be reliable. So that's why we have to put in those variables that are important if the equation does need an intercept term, or there is a trend, or you identify, oh, there is some autocorrelation problem. By adding the lag terms of yt, that's an effective way to remove autocorrelation issues in the residual terms. Next is the critical values of DF test or Dickey-Fuller test. Although it looks like we are performing a t-test, but in fact it's not, because it violates the variables are potentially not stationary. It violates the basic assumption of those t-tests. So there's some complex procedure to derive the correct critical values for those tests. But good news is you do not have to go through those process. All those critical values are given in either software or textbook. And on the slide, I give you the critical values for different model specification. So the first one is a test model. That's Dickey-Fuller test. Test model without an intercept term, without a trend. You have a critical values corresponding to the 1, 5, and 10%. Then, if you believe that there should be a trend, should be a drift, or an intercept term, you need to use the second equation to calculate the value of gamma, and that the critical values will be different. And if you add a trend term into your test equation, that will change your critical value as well. And in the last row, those are the standard critical values from a t-test. Don't use them, they're wrong. And you can see how how big the difference is between the standard critical values and the correct DF test critical values as given above. The procedures to perform a DF test is to start with a time series plot. So we observe the pattern, then we decide which test equation we should use. Do we need an intercept term? Should we include the trend? For example, if the time series appears to be wandering or fluctuating around a sample average of 0, then that's an indication of a zero intercept term or a test equation without intercept term. However, if it is wandering around, but it's around a non-zero mean, that's an indication we need to include an intercept term. If there is a linear trend, upward or downward trend, then we need to add the trend part, the lambda times t part, into the test equation. Then we go ahead and estimate the value of gamma to perform the test. Let's use one example to demonstrate how to perform the test. So we use the federal funds rate and the 3 years bond rate as examples. And the test equations are given on the slide because based on the time series charts that we examined before, both of them seem to wander around a non-zero mean, but it's not clear that it's a linear trend. So it is not going up or going down clearly. So we use the test equation with a drift or an intercept term, but without a trend. We also include the lag term of the dependent variable just to account for the potential autocorrelation problem. And because we use this test equation, the 5% critical value is negative 2.86. So the test statistics are calculated and given on the slide. And for both of them, they are they're larger than the critical value because the absolute values are smaller. So we do not reject the null hypothesis. Both series are not stationary. Remember, the null hypothesis is rho equals 1 or the gamma is equals 0. So both of them are stationary, which is consistent with the pattern that we observed from the time series chart we saw before. Then the next step is to calculate the first difference of both series. You may still recall that the time series chart of those two different time series are very stable and they fluctuate around the mean of 0. So this is why for the test equation, we do not include the intercept term and we don't need the trend term. So it's just the variable itself. And the test statistics are much larger. The absolute value is much larger than the absolute value of the critical value. And both of them are obviously in the reduction region. So we reject H null and we conclude that the first difference series are stationary. So it's time for us to introduce another new term. If a series can be made stationary by taking the first difference, we will say that this series is integrated of order 1 and the notation is I1. So if somebody tells you, oh, this variable is I1, that's a fancy way to say the original variable is not stationary. But after taking the first difference, the first difference variable is stationary. And the stationary series are said to be integrated of order 0 or I0 or I null.